So, good morning, everybody. Thank you for joining this for lecture about the new European Bauhaus series. Today we have the pleasure to host Professor Ambrose Dodoo of the Department of Building Technology in Linnaeus University. Um, Today's lecture will be the Wood and Solution to Timber Buildings for Well-being and Climate Resilience. So wood is a sustainable construction material that stores carbon and improves indoor comfort, partly due to its moisture regulating properties. Climate change will increase cooling demands and overheating risk in buildings, making energy efficient design strategy essential for maintaining comfort. So thank you, Professor, and then I will let the floor to your presentation. Thank you.
Thank you very much, Alberto, and welcome all of you. Good morning to this lecture. It's a pleasure for me to give this lecture, and I'm very grateful that you are present to listen to what I'll present. And as Alberto introduced me, my name is Ambrose Dodoo, and I'm a professor of building technology at Linnaeus University. And today I will present lecture 4 on the wood solution 2. Yesterday, my colleagues presented on the wood solution 1, which I think should also be online, I think, at later time for you to also connect to that. And that lecture focused more on the material, of course, wood as a material. Today, I want to look at the environmental aspect of wood, and then also to talk about wood for climate resilient and well-being. I mean, wood building for climate resilient and well-being. And my lecture will follow this outline. I will start with a bit of background about the global energy supply and then associated climate impacts. And then I will connect this to why life cycle analysis is a very important tool for us to design our buildings to reduce resource use and also to reduce climate impact. And over here, I will also show the climate impact of wood and non-wood buildings from a life cycle perspective and why the use of wood is very important for climate change mitigation. And then I'll also give a bit of synthesis about the wood impact on indoor environmental quality based on current research or the current state of knowledge. And then I'll also talk about the impact of climate change on wood buildings, focusing on energy demand and overheating risk, which is very important for well-being. And then I'll end with some concluding remarks. And I hope we can also have some discussions based on what I present today. So this is the starting point of this lecture. If we look at the global primary energy supply, we see that we are heavily dependent on fossil fuels. We see the evolution of the global primary energy supply from 1990 up to the year 2023. That is about 33 years. And in absolute terms, we see that the renewable energy, as we see over here, or renewable energy, so we talk about this green, and then we also talk about this biofuel again. This has increased over the years in absolute terms. This is what we have in 1990, and then this is what we have today. But if you look at that in percentage-wise, we see that still we are heavily dependent on fossil fuels. Globally, over 80% of all our primary energy supply is still coming from fossil fuels, despite all the effort we continue to make. And of course, we are making a lot of effort. So this tells us that we need to do more than what we are doing. This is because our use of fossil fuels is associated with carbon dioxide emissions. The fossil fuels are hydrocarbons. In other words, when we burn them, we get carbon emissions and we also get hydrogen coming into the atmosphere. And we see the evolution of the global carbon dioxide emissions over the years. And this is actually following our consumption of the fossil fuel. So this is a reflection of our global energy and material system that we have today, that they are heavily dependent on fossil resources or fossil fuels, as we see over here. Over here, we also see the emissions, which is also coming from land use change. Of course, this is when we clear the forest or when we change the use of land, and then carbon is emitted. Together, we see that the emission is increasing, and we need to change the current trends. And already we see that today, global emission has caused temperature increase of about 1.4 degrees Celsius if we compare that to the pre-industrial era as we see over here today. And even if you look at the latest numbers, we saw that in the year 2025, for the first time, the temperature, anomaly or the temperature deviation for a particular year, that is for the year 2025, was over 1.5 above the pre-industrial level. So we face a very huge challenge, especially when we have a global ambition to limit global warming to well below 2 degrees while looking at 1.5 as our target. Over here, we see that even if we cap emissions, if we maintain the same level of emission we have today to the end of the century, we can still not come to the world below 2 degrees. The option we have is to go net zero emission. And even if we talk about net zero emission, time is of essence. And over here, we see two options we have. What if we go for net zero emission, for instance, from this year, the year 2026? Then we will come to about 1.5 degrees, which is what we aim for. If we choose to go for net zero, that is all our emission is net zero from the year 2050, as we see over here, they will go to about 1.7. So we'll still not be able to get the 1.5, but at least we'll go below 2 degrees. So the current way, we supply our energy, to power our production system, to produce our materials, needs to be rethought or needs to be rechanged. This demands fundamental transformation. And the IPCC 1.5 report, give a number of strategies we can implement to achieve this 1.5 if this is what we want to achieve according to the Paris Agreement. And of course, we have different strategies for different end-use sectors or different sectors where energy is used and emission comes from. And for the building sector, this is one of the things the report said, which I have highlighted over here. It said 1.5 degrees consistent pathway requires building emission to be reduced by 80 to 90% by the year 2050. And this is a very big challenge. New construction to be fossil-free and near zero by the year 2020. This is an enormous challenge. The question is, how do we achieve this in the building sector? What are the solutions to achieve this kind of high ambitions? Of course, these are not only high ambitions, these are challenging, but this is something we must do. It's an imperative, it's a demand for us to do. And of course, we can also look at our end-use energy sectors. In Europe, we can look at it from the world. And if you look at it, the pictures are still the same, that the building sector is where we use most of the energy. And as we have said, most of our energy globally is coming from fossil fuels again. And even in Europe, most of the energy is coming from fossil fuels still. And about 36% of all our emission is also coming from the building sector. So reducing emission in the building sector is also, from a sectoral perspective, this is very important. But how can we achieve this 80 to 90% decrease in the emission from this sector? What are the strategies? What should we do? And over here, we can also look at the emissions, from the building sector in the European Union. And I also want to show the picture of Sweden, because we have a figure for the European Union, but when you also look at countries, you might also see some little differences in these emissions. And over here, we see the light blue and the deep blue. This is the emission from the building sector in the EU, for instance, which is about 36%, nearly 40%. If you look at Sweden, again, you also see the emission from the building sector over here. Today, it's about 20%. But if you look at these numbers, you can see that we have both embodied carbon emission and operational carbon emission. The embodied carbon emission is the emission from the production of construction materials and the construction process. To transport the materials to the construction site, to assembly that, and then to demolish that. And then the operational is the one for heating, for ventilation, for cooling our buildings. So from an European perspective, you can see that from the building sector, about 1/3 of the emission is coming from construction materials and 2/3 is coming from operational. Now, if you also look at Sweden, the picture is a bit different. You can see that in Sweden, most of the emission is coming from the construction materials. It's about 57% from construction materials, only in the building sector. And then the other 47 is coming from operation of building or operational phase. And this is because in Sweden, the energy system for heating buildings, for electricity is based on low carbon fuel. So what has become dominant is the construction process, which depends on very fossil intensive materials like steel, concrete, and also, of course, the trucks to transport the materials, which are based on diesel and other things. And these are strategies, I mean, we have to think about. How do we reduce the emission from construction process? How do we also reduce the emission from the operational process of buildings? And over here, life cycle thinking is very, very important that we look at strategies which can reduce both the embodied carbon from the construction process and also from the operational carbon from the operational process. And for the embodied carbon, for instance, we can look at better designs. How do we design, I mean, more resource efficiently? And over here, we need, for instance, tools to help us to design more efficiently. And one of the tools is life cycle analysis or life cycle assessment, which I'll talk about in the context of food construction. We also need alternative materials. Today, most of our construction in Europe is heavily dependent on steel and concrete. And we have to explore the possibility of using other materials, other more renewable or low carbon materials, for instance, wood and for instance, clay and so on. And then the conventional materials like steel and concrete also, we also have to decarbonize them because when you have wood, for instance, when you have wood buildings, we also have foundations which are typically made from concrete again. When you have wood construction, most of the connections are based on steel. So even for wood buildings to get low carbon footprint, other materials must improve. So we have to look at a system-wide thinking, not just only one material, but to decarbonize all the materials and also minimize our need for heating and cooling. And this cooling is very important in the context of climate change, which I'll show currently, because today the cooling demand in Europe is low, but under climate change conditions, we expect temperatures to rise and cooling demand might increase significantly. And this we have to also look at. So life cycle, when we want to use life cycle analysis as a tool, I mean, to optimize and design our buildings to reduce primary energy use and also to reduce emission, we need to look at the entire chain, that is from extraction of materials to the end of life of the building and even recycling and reusing the building. And commonly we do the life cycle analysis by following the European standard, the EN 15978. And this prescribes an approach to do life cycle analysis of buildings because doing an LCO, life cycle analysis for a building, is different from doing that for a product. For instance, if we take a product, I have a bottle over here. This bottle might last a year or maybe less than a year. So we know the end of life. But buildings last longer. We have buildings which have stood 700 years, still standing. You look at the average life of the building stock, for instance, it's between 80 years to 120 years again, worldwide. So these numbers vary. So how do you, for instance, give scenario about what is going to happen at the end of life of a building? What is going to happen? So this demand a more careful approach. It's a very complex issue, and this demand a more careful approach. That's why when you do life cycle analysis, we have to follow the standard. And when we talk about life cycle analysis of buildings, we distinguish between two main aspects. We talk about the embodied carbon, which I talk about, for that is for the construction process. And this is what we see, for instance, A1, A2, A3, A4, A5. And then we see B1 to B5. These are all embodied carbon. This is associated with the construction process or materials. And then we also have the C1 to C4. And then we also have the operational carbon, that is from the use of the building, from heating, from ventilation. And when you do an LCA, we need to show both of these, because sometimes you might end up optimizing one of them and then influencing the other. And then in the end, you are not saving from the life cycle perspective. So a good LCA should optimize both the embodied and operational carbon. And I'll show the consequence of this when you look at wood buildings. So I just want to show a series of studies, and then I'll show what synthesis of literature show in the context of using wood for construction. So this is an LCA study we did a couple of years ago. And over here we have a reference building, which is a concrete frame building, a precast concrete frame building, which is built in Sweden in the city of Växjö, where I sit today. And here we engage construction companies which are building with wood to design this same building with a wood building system. So they have the same They took the same floor plan, the same wall, and then they designed these buildings to carry the same load. So we say that, and then to give the same heating demand. So the buildings are designed to be functionally equivalent or thermally comparable. So they can take the same load and they give the same heating performance. And then we do an LCA to compare where does this building stand in terms of resource use and in terms of carbon dioxide emission. So this is the original design of the building, which is built today. And then this is when the building is designed with cross-laminated timber, which is a form of massive timber over here. And then we also have a modular timber where we have timber volumetric elements or light timber volume elements, which are also assembly on site. So we have different wood construction. So this is a wood construction, light timber wood construction in the form of a volume element. And this is a massive penalized wood construction based on cross-laminated timber. And then this is a concrete. So to do an LCA, we first start by counting the mass of the materials in the building. And over here, we can see the mass of the different materials. We can see that concrete, is a dominant material in the concrete frame building. And this is obvious. And we also have concrete in the wood building because the foundations are made from concrete as well. That's why I say that to reduce emission in the construction sector, all materials must be decarbonized, not only, wood, all materials over there. So this is the mass of the materials. And then based on this mass of materials, we calculate the energy to extract, to transport, and to process these materials. And we can get the primary energy use and also the emissions. And over here, I want to show some few numbers about the primary energy use. So this is the energy to extract, to transport, and to process the building, and also to construct it on site again. So this is the primary energy use, which reflects the use of natural resources. So we can see that the concrete frame building requires much more primary energy use than the wood building. As you can see, it's at least, if you compare this to this, it's about 1/3 more, as we can see over here, for the concrete building compared to the cross-laminated timber building. And it is lower for the modular timber building, as we see over here. Now we can also look at the embodied carbon. That is the embodied carbon just for the production stage. So over here I talk about A1 to A5. And we have for the material production, that is to extract the materials, to process it, and then to transport, and then to build the building. And then we also have what we call the cement reaction, which is coming from calcination of cement, and then also carbonation. When you talk about cement production, I just want to mention one thing over here, that the emission from cement production is not only from fossil fuels, it also comes from a chemical reaction called calcination, when the cement is made from limestone, because this limestone is heated or is cooked, and then it breaks down into calcium oxide or clinker and then carbon dioxide. So we get process-related emission. And sometimes we want to show this differently, because for the material production in construction, these are coming from fossil fuels, but then cement reaction, you also have chemical process, which is producing this emission. And of course, you have more for the concrete building because you have more concrete over there. But what we saw in this life cycle analysis is that when you build with the wood-based construction or systems compared to the concrete, the emission is reduced about 47%. So building with wood gives lower carbon dioxide emission. And these are studies we have done. And I want to put this in the context of the literature, because other people have done studies. Have they come to similar conclusions as we have come? And I will say, yes, this is an example of a study which is also peer-reviewed. What our studies are also peer-reviewed. And over here, a concrete building as a reference building is compared to different wood construction systems. And the buildings are shown over here, as you can see. So this is the A is a concrete building, as we see over here. And then we also have light concrete building mixed together with the wooden elements also mixed over there. And then we also have the cross-laminated timber building also over here. That is a massive timber building. And I want to focus on the conclusions of this study. Over here, we can see this D and D, which are the wood solutions, right? And then this is a concrete building. These are the concrete building systems. If you look at the emission difference between this, it's about 1/3 again. So we see about 1/3 difference, so about 33% reduction in emission when you use the wood-based system instead of the concrete build system, which are the A and B, as we see over here, at least over there. So we also see a similar trend of results that building with wood results in lesser emission than building with non-wood materials. So these are wood and concrete I've shown so far. What about steel? Steel is also an alternative material. And over here, this is a study which was done in the UK a few years ago. And over here, the buildings are also designed to be functionally equivalent. An office building or commercial building in steel frame, in concrete frame, and in wood frame. And over here, you can see the carbon footprint, the embodied carbon for the construction process. Of course, when you just look at A1 to A3, which is just the production of materials, or you look at A1 to A5, which is just, the production, the construction, and then you look at A1 to C, which includes the end of life, or you look at the D, which also includes the end of life benefit. And over here, we see an interesting thing that if you only look at the production phase, or you look at the product stage, the wood has significantly lower emission for all scenarios. And we have different configuration of the wood building. This is the timber building as it is. And then this is when you have timber buildings, but you have bioenergy capture and storage. That means when you, for instance, you burn the wood at the end of life, you have like a carbon capture and storage to take the emission again, so it doesn't go into the atmosphere. And then this is when we don't have sustainable forestry. That is, we cut the wood and we don't plant it. This dark blue shows that the wood is cut and then we follow sustainable forestry practice like the way we do today. Because wood, I mean, today we know that wood today in Europe is certified when you are going to buy that is coming from a sustainable forest. But if the wood is not coming from sustainable forest, that is no replanting, we see what is happening. Now, if you look at A1 to C, you see that when the wood is coming from sustainable forest, we have significantly lower emission for the wood compared to steel and then to concrete. That is 206 compared to 397 and 311. But if the wood is not coming from sustainable forest, that there's no replanting, that means the emission of the wood building is slightly higher, I mean, compared to the concrete building, or a little higher. And again, we also see the A1 to D. So one of the fundamental things for us to realize the climate benefit of wood is that the wood should come from a sustainable forest. This is a very fundamental thing, that the wood should come from a sustainable forest. So this is the condition under which wood perform better than other materials, that the wood is coming from sustainable forest. Now, I also want to show a study which focus somewhat on the operation phase. So far, I've just shown mostly on the A1 to A5. I've also shown the end of life, or the embodied carbon, but I have not shown the impact on the operational carbon. What does it mean to build with, for instance, wood instead of concrete when you look at the operational carbon? Because we know that concrete, for instance, has a higher mass, or the thermal capacity, or the more thermal mass than the wood building. Does this play a significant role if the buildings are designed the same? So in this life cycle analysis, we looked at a building which is built in wood, but it's also designed in concrete to be functionally equivalent once again. So they are designed to take the same load, to give the same floor area, to have the same U value, the same level of insulation of these buildings, and then we compare them. So over here, the focus is on the primary energy use, that is the energy to extract, to process, then to construct the building, and then to heat the building, and then the end of life. So we look at the entire energy chain, or the resource chain, to look, does it really matter when we build with concrete and wood if you also consider the operational phase, or the thermal mass effect of concrete over here? And this also came from a peer-reviewed study also. So this is the mass of the material of the building, which I will not go so much into. And over here, we can also see the primary energy balance of the building, the focusing on the production phase. Over here, this is the material production, that is A1 to A3. This is the on-site construction, that is A4 to A5. And then this is also the wood residuals we get from the wood construction process. And we see the net balance over here, that the wood building has lower primary energy use or resource use in the production stage compared to the concrete building. what we wanted to actually find out over here is the operation phase or the operational carbon. And over here, we have the building heat demand or the building heat load. So this is a form of heat load duration curve for the building. And here we see the demand or the need for heating of the building during the winter season. And then over here we see spring and then autumn. And we see over here, for instance, this is a building as it is built today. And we have the wood frame building, which is the solid lines, and then the concrete frame building, which is the dashed line. So all the lines, there are two lines over there for each of the lines you see. We have when the building is designed as a passive house with a lot of insulation or adequate insulation, and then the reference building, which has lesser insulation because it was built in the mid-1990s. And then when you build a building to, for instance, the Swedish Building Code of 2009, around when this study was done. Now we see that if you look at for instance, the reference building over here, at the winter season or the peak heating season, we don't see difference between the two lines, meaning the heat demand of the concrete building and the wood building are the same. But in the spring, especially when we have more solar energy in Sweden, or where we did this study, they will find slight difference between the concrete frame building and the wood frame building, even though they have the same U value. And this is because of the thermal mass effect. Now, you also look at the same phenomenon when you look at the wood frame building and the concrete frame building when it is designed to the passive house standard, which has a lot more insulation. Then you can see that you don't even see the difference between the wood frame building and the concrete frame building in the operational stage of the building. So the conclusion is that if the building is designed to a very energy efficient level, then a wood building and a concrete building have the same performance in the operational phase again. So this is a very important conclusion we have over here. And this is the buildings, again, we see the whole operational energy of the wood building and the concrete building, the buildings I have shown. It doesn't really change so much, especially when the buildings are designed to be very, very energy efficient with a lot of insulation. So the critical thing when you compare wood and concrete building is actually the production stage. If all the buildings are designed to be thermally comparable or they are designed to the same standard, the use phase is about the same for them if the buildings are well insulated. And this is the end of life of the building also, which I will not go so much into. But what I want to just present over here is a synthesis. What does the literature show? So I have shown studies we have done, and I have also shown studies from other researchers. What we also try to do is also to look at CLT, which is a modern way of building, medium to high-rise wood buildings, and then compare this, to other building systems from the point of the literature, when you look at the literature. So over here, we look at different studies, over 30 studies which have been done comparing LCUs of wood, that is CLT based on cross-laminated timber, to steel and then to concrete. So we have compared this from the literature. So the studies we compare must have these two. They are comparing CLT and then wood or steel. And I want to focus a little bit on the abstract, what is written in the abstract. So this paper, you can get this paper online as well. So this is a key thing from this study, that on average, we found that there is about 40% reduction in carbon footprint when we use cross-laminated timber, which is a massive form of wood, compared to when steel or concrete is used for the same multi-story building. This is what we came to, again, from the literature. So building with wood gives climate benefit, if you look at it from a life cycle perspective. And when you build with wood and you build with concrete, and the buildings are designed to be thermally equivalent, then there is no difference in the heating demand during the operation stage over here. One of the things I've also tried to look at in this lecture is also to look at the indoor environmental quality. And over here, I draw on the literature, a study which will synthesize many studies which compared wood, used in construction, that is mostly in the internal, I mean the finishing of the buildings, or exposed wood in the construction. And as you can see, this is a very extensive study covering about 140 peer-reviewed articles and also PhD dissertations and books. And I just want to draw on the abstract again, or the key conclusions, that when you build with wood, of course, you have a positive or neutral effect on the indoor environmental quality mostly. That is humidity, you have indoor air, and then positive feeling from the occupants. So this is what this study is showing if you look at synthesis of literature. Of course, there are also other issues like you also have like a formaldehyde and also other emissions. I mean, especially when you have glued wood or painted wood, which is exposed indoors. But mostly the studies show positive or neutral effect of wood use in the indoor environment. And of course, the study point to the need of more studies in this direction again. I also want to discuss a little bit on how climate change would affect energy use and thermal comfort in modern timber building systems. So far, I have discussed extensively or more on how to decarbonize the building sector, which is very important for us to reach this 1.5 or well below 2 degrees. We know that most of the emissions are coming from the building sector. So this is what we are doing. We have buildings which is affecting the climate or destabilizing the global climate system. And we know that climate change is also going to affect buildings. So we need to mitigate climate change by adapting solutions which reduce greenhouse gas emissions, like wood as a solution. And this is very important. But at the same time, temperatures are rising, and we know that climate is changing. Our climate elements like humidity, rainfall, snow, these are changing, and these are going to affect performance of buildings again. So we also have to adapt our buildings to climate change or future climate change conditions. And we have looked at this question in the context of wood buildings as well. How would climate change affect energy use and indoor environmental quality, especially thermal comfort in modern timber buildings? And over here, we look at two timber buildings. We have a cross-laminated timber building and also a light timber frame buildings. What we did the LCAs on, we have done LCAs on this. And one of the things I want to point out is that these buildings were built in different areas. You have the CLT building, which was built around 2009, and then this light timber building, which was built around 1994. And you can see their U values, which reflects the demands of the building code during that time. So over here, we are not directly comparing the buildings, but we want to illustrate the effect of climate change on the performance of wood buildings, not just we are not comparing the buildings, but how climate change affect the performance of the buildings again. And for this study, we have used what we call the representative concentration pathway climate scenarios from the IPCC, or the Intergovernmental Panel on Climate Change. And these scenarios propose different pathways, I mean, on how the global climate system is going to be, depending on where we choose. We have the dot lines over here, which shows our historical emissions. And this RCP, for instance, 8.5 shows that if we continue the path we are going, then by the end of the century, temperature is going to be about 4.9 degrees Celsius, averagely, right? So this 8.5 is just what we call the radiative forcing. That is the balance between the incoming and outgoing radiation. So if it is more, it means that we are trapping more heat. And if we try, I mean, to reduce emission, and if you want to go for the 1.5, then around the mid, for instance, 2020s, we must always already have peaked, and then emission will begin to decline. Then we go to 2.6, which means we have less warming, that is less trap radiations on the earth. We have looked at these scenarios for the municipality of Växjö. So this is how the different RCPs translate to the municipality of Växjö, for instance, in the south of Sweden, as we see over here. So this is 2.6, 4.5, 8.5. So if you go, for instance, the worst form of climate change, we expect the temperature in Sweden or in Växjö to be around 5 or nearly 6 by the end of the century, as we see over here. RCP 2.6 is giving us, for instance, lower about 2 degrees. So we have used this to do energy simulation of the building. And over here, we have used the 1996 to 2005 climate as our reference or our baseline. And then we have used a methodology which is called morphing, to stretch the historical data to produce, for instance, how the climate is going to be in future again. So, and then based on that, we have done simulation to calculate how the indoor climate is going to be in terms of temperatures and also the energy demand of the building. And here we have used a dynamic simulation program called VIP Energy, which is commonly used in Sweden. And we also see the simulation input data, for instance. For this study, we have assumed that the indoor temperature in the building is about 22, and this follows the requirement of the building code again. And over here, this is the apartment areas, and then we also have the common areas. In the common areas, you have like the stairs or the laundries, which is for common everybody, in the building again. So the temperature there has been set a bit lower. And then we also have the cooling set point, the point at which we begin to cool. And this is also based on the regulations in Sweden, which says that overheating starts when temperature exceeds 26 degrees. We want to avoid overheating. So this is the cooling set point we have set over here. Of course, in some countries, the cooling set point might be different, but here we have tried to use Swedish data again. And we have assumed that the building is occupied all year round because it's a multi-story building. Some people might go to work, but some people are still in the building again. And this building has, for instance, a central heating system, which is district heating again. So this is the annual final energy demand of the building if you look at the baseline climate. And of course, we see that the CLT building has lower space heating demand because it has better U value and it was built to the modern standard compared to the light timber frame building. That's why I said we cannot literally compare the two buildings, but we can just see how climate change is going to affect their performance once again. So over here, what we want to look at is the space cooling and the space heating load. And I should say that typically in Sweden, we don't have space cooling systems in residential buildings because the cooling demand is very low. Normally, we induce cooling by increasing the airing or the ventilation rate in the buildings or opening our windows again. But we have heating systems. Of course, Sweden is a very cold place. So we look at how climate change is going to affect the balance between space heating and space cooling. And over here, we can see the baseline. This now is a cross-laminated timber building, and then this is the light timber frame building. So this is a baseline, which is 100% where we started from, right? Look at the RCP 4.5 and then 8.5. This is the year 2050s. That is from the year 2050 to the year 2059. And then this is the year from 2090 to the year 2029 again. So over here, this one is showing the space heating as we see over here. And then this is showing the space cooling. We see decrease in space heating demand of the buildings that we go to about 40% decrease by the end of the century if we go for worst form of climate change. Even the moderate or the medium climate change is going to reduce the heating demand of buildings about 20%, as we can see over here. And then we can also see the cooling demand. This is the baseline cooling demand. And if you go for the moderate climate change, we are heading about a 50% increase, almost 50% on average by the middle of the century for the middle climate change. And then we go even more. If you look at the worst form of climate change, we are going to about 400% increase, or a factor of 4, as we can see over here, the worst form of climate change over here. So the trend we see is that if you look at wood buildings, not only wood buildings, every building, you see similar trend, that climate change is going to cause the heating demand of buildings to decrease, but cooling demand to increase. So even though wood is a very good material to build with, we should also think about how we design our wood buildings to reduce the need for cooling, especially under climate change scenarios, again, over here. This picture is showing the indoor temperature profiles of the buildings again. This is the light timber, and then this is a cross-laminated timber again. And this is the worst form of climate change. This is a hourly temperature. You can see we are getting to about 42 degrees over here, and over here around 38 degrees. So this is a hourly temperature for the year. What we are concerned about over here is to look at the risk of overheating, which is very important for well-being, because when the building is overheated, that affects our concentration. That is not good for children and elderly, I mean, who are very sensitive to this kind of temperature. I mean, so this is a well-being issue. So as I said, in Sweden, when the temperature exceeds 26 degrees, we say that the building is overheated according to our criteria in Sweden. And you can see the indoor temperature of the buildings. This is a cross-laminated timber building, and then this is the light timber frame building. This is where we have the medium over here, the medium value. So this is the medium value we have over here. In the baseline, we are around 25 for the medium, which is good. But if you also look at, I mean, the whiskers or the top over here, you can also have a temperature going as far as 35 degrees in summer, which is not good for well-being. And we can see that the situation deteriorates or it gets worse, I mean, under the climate change conditions, especially the RCP 8.5, which is the worst form of climate change. That is, if we continue to design the building the way we do without interventions, we don't do anything to reduce the indoor temperature. And this is also the light timber frame building. We can also see that we also see the overheating threshold. We go beyond 26, even in the medium temperatures, as we see over here. These are no interventions. So we have also looked at interventions. What if we do measures to actually reduce the indoor temperature? And one of the things we have looked at is airing. That is, we increase the ventilation rate as we commonly do in Sweden. Today, the building code says that the minimum ventilation rate in Sweden is about 0.35 liters per second per meter squared. That is about changing half of the air if you have a room height of about 2.5 every hour, or 0.5 air change per hour for a room height of 2.5 meters again. So we double that, or we can also have solar shading. That is, we put shading devices on our openings or the windows or the doors to cut the solar radiation coming in to the building. And over here, we can see the baseline. These are the baseline, right? The temperature. These are the baseline, and then these are the climate change scenarios. So the baseline is from 1996 to 2005. We can see the percentage of overheating hours of the building. Anytime we exceed 26 degrees, as we say, it's overheating. So if you look at the baseline already, the building is slightly overheated about 10% of the time. But if you go to RCP 8.5, which is the worst form of climate change, overheating is going to increase about a factor of 3 without intervention. That is when you don't do airing, when you don't do shading of the building. But if we do solar shading, as we see over here, or we increase the airing, or we combine the strategies, we can see that overheating is significantly reduced. This is no intervention. Look at this, and then you compare this to this. This is reduced drastically again, and then you can also compare this one to this one. When you combine the two measures, overheating is decreased. We also see the same trend, I mean, for the light timber frame building. And what this is telling us is that when you design timber buildings, we should also look at strategies also to prevent overheating of these buildings, and more especially passive strategies. This should be incorporated in the building already, because these have effect on the cooling load, which I will show slightly for the buildings. Now, this is a building with interventions, once again. So these are when we do interventions. If you watch the previous chart, I mean, where I showed a similar box diagram, we can see that the medium was around 25 degrees, I mean, even for the baseline. But over here, we can see that even under climate change, that is in the middle of the century, we are coming to 25 as a medium temperature over here. And then the worst form of climate change, we go to the medium of maybe around 26 or a little bit over, because we have applied intervention strategies in the building, as we see over here. We also see similar trend over here, that when you apply intervention strategies to reduce overheating, then we can get very comfortable in the indoor climate in wood buildings as well. Now, this is what we also see for the cooling load again. So this is a baseline when we have the initial, that is no intervention in the building. And then when we have the intervention, when you combine herring and then shading, we can see that we reduce the cooling load quite a lot in the building again. And this is what is interesting over here. This is the worst form of climate change. That's the RCP 8.5. If we combine these intervention measures, you can see that we reduce the cooling load quite a lot to the baseline without intervention. So this is telling us that even under the worst form of climate change, of course, which we should try to prevent, we still need measures to reduce our cooling load. And this will take us to the same values we have for the baseline without intervention. Again over here, and we see a similar trend over here. Of course, this one over here, we see that, of course, even though we reduce that, we don't come to the level of the baseline as we see over here. So what I want to point out over here is that it is resource efficient and carbon efficient to build with wood as a construction material. But we need to adapt strategies to reduce overheating in wood buildings, not only wood buildings, but all buildings again. Because we might end up, building with wood, saving resources, saving emissions. But if we don't do strategies to reduce cooling load, then we are going to increase our cooling demand in these buildings. And then the resource gain we get, is going to be offset by the increase in cooling load, because our cooling load is mostly delivered by electricity today. So I just want to conclude this lecture by saying that wood-based materials reduce embodied carbon and support decarbonization of the building sector. And climate change shifts the energy demand of buildings towards more cooling in the Swedish context, but not only the Swedish context, the Nordic and many European countries as well show this again. And increasing, indoor temperatures in the buildings leads to discomfort, and this affects well-being. And this is something we should expect under future climate, unless we do strategies to reduce our cooling load or indoor temperature. And over here, we have passive strategies like solar shading or awning, which can cut the overheating of our buildings. And this we should try to incorporate in wood buildings, with all buildings when we design them today. And we can also do the same buildings to the same thing to existing buildings again. So in conclusion, I would say that timber buildings support low carbon society and should be adapted to future climates to enhance well-being and resilience. So this is my last slide, and I just want to say something from the Intergovernmental Panel on Climate Change. The assessment report says that the climate we experience in future depends on our decisions today, how we build today, the kind of walls we use today, the kind of materials. And the science shows that building with wood results in less emission than alternative materials if the buildings are designed to be functionally equivalent. And I also want to say something from the United Nations Environment Program, from the unit called the International Resource Panel, where I'm also a member, that we need to bend the trend. Emissions continue to increase. We need to change the trend, and we can bend this by adapting the solutions we have. We have solutions like building with wood as a material, to reduce carbon emissions. And we need to adapt these materials, implement them to create a healthier planet. Thank you very much.
Thank you very much for this very stimulating presentation. Or do you have any question?
Yes, Emily.
Thank you. I have a question in terms of scale. So, especially in a lot of cities, we are seeing that we don't have enough housing. there are some limitations on even on CLT for scale of buildings. Do you have a perspective from your research around at which point we don't look specifically at the scale of the building in terms of how to use timber versus concrete, or at which point we will make different decisions based on overall housing needs, um, and how our decisions about how to build our cities are making are really challenging us around building at scale. So it's a how do we get the scale we need and still build thoughtfully about the future that we are building for ourselves?
Yes, I will respond, and I think my colleague Stefan will also have some points over here because he also works a lot on this kind of question. So what I will say is that, I mean, it's very important to look at this question. What you said is true. I mean, we need to, there is more demand for housing. We need to build more facilities. And again, we have to look at this from a regional context. And if you look at, for instance, from the Swedish context, you look at it from a European context, I mean, the forest growth is more than the harvest. From that perspective, I mean, we can get more wood from our forest, for instance, to supply CLT and other wood-based materials, I mean, to construct our new buildings. So the resources are there. As I mentioned, I think sustainable forestry is fundamental, I mean, to the use of wood. So whenever we are using wood, we have to ensure that the wood is coming from sustainable forest. And from the Swedish perspective, from the Nordic perspective, and from the European perspective, that is not a question because the forest is managed sustainably, and then the growth is more than the harvest. So this, we have the resource to make. But then when you look at it from the global scale also, I mean, you also have to look at, I mean, the situation of forest in different parts of the world. I mean, I will say that there is no point using wood from a place where the forest is not managed sustainably, because this is going to increase, I mean, the emission from the land use change. And this you want to avoid because this is still significant globally. I mean, it's about 10% again. So I will say that in each region, I think the material which is available and sustainable should be used over there. In some regions, for instance, clay is available, other renewable materials is available, and this should be used. So I will say that I will not say that every region should use wood, but every region should use the material which is readily available and which is also sustainable again, because this is also in the interest of national security. I mean, there is no point, I mean, choosing sustainable material from another country when there can be disruptions in the supply chain, as we see recently. I mean, if you have a project which has to be delivered, and then we don't have the resources because, I mean, the ship path is blocked, how do you get it again? So national security is very important. Sustainable forestry is also very important. So this is what I'll say. But maybe Stefan, you have a point to make.
No, it's just that there is enough growth in the forest to supply all construction in the world. But I completely agree with Ambrose, and I also think that we in the numbers that you have shown, Ambrose, you're still counting on the foundations made by concrete and a lot of unsustainable materials. So you can get your buildings with very easy measures to be a lot better than the buildings that you have been showing. So, and yeah, it's also, I think it will very soon reach a state where where timber buildings are cheaper than concrete buildings or brick buildings or whatever, especially if we also have to price the carbon dioxide that is emitted in the production.
Thank you, Emily.
Thank you. Are there any further questions? Or comments? Oh, Felix. Yes, please. You want to intervene?
You mean a clap?
Ah, sorry. I thought you had the hand on. Okay. Okay. So, thank you very much for this lecture and presentation. It was very inspiring and stimulating. So, I will give you appointment to the next lecture. That will be in 1 week on Tuesday at 10, same time. Will be hosted by Professor Valeria Lingua of the University of Florence with the title The European Urban Agenda into Practice, Regional Design for Transformative Cities. And that will be the ending of the lecture series. Then, as an ending note, I will invite you, for those of you that would like to participate at the New European Bauhaus Festival, to send a presentation or a small pitch video, or also a concept note, 1 or 2 pages, about a project, individual project that you would like to present. The first 3 placed will have the opportunity to go to Brussels with all costs covered by the project. And thanks to the Linnaeus University, we'll have a dedicated stand to present. Can be a poster or just material or something also practical, something like just an oral presentation or something that you would like also to create to present at the festival. So thank you very much. And if you want to, you can send to me to my email the project, and I will be happy to then send to the committee for a review. Thank you very much. Thank you,
Very
Professor
much.
Ambrose Dodoo. Thank you, Stefan Schartner. And we will see you in 1 week on Tuesday, the 28th of April. Have a nice day. Bye bye.
Thank you very much. Thank you very much for listening to the lecture. Thank you very much. I'm grateful.
Thank you. Bye.
Bye. Bye.